Hi, everyone. So this is the last lecture of this quarter, and I would like to talk a little bit about atoms, because no discussion, no introduction of quantum mechanics is fair without at least mentioning atoms, because the study of atoms and the study of atomic spectra was one of the main driving forces behind development of quantum mechanics. Although I must reiterate, quantum mechanics is not necessarily specifically about atoms, but atoms provided an early driving force behind development of quantum mechanics, and it's still continuing to develop in some form. We saw that one of the hallmarks of quantum systems is the fact that energies come on a discrete spectrum. So some students still don't understand what I mean by the word discrete. So when I look up the Google definition of the word discrete, it says individually separate and distinct. So we saw example after example of energies in quantum systems being individually separate and distinct. Particle in a box, particle in a finite well, harmonic oscillator, they all have individually separate and distinct energy levels. Energy 1, 2, 3, 4, but nothing in between. So that's an example of discreteness of energy, which contrasts classical situation where energies fall on a continuous spectrum. We also saw that scattering states in quantum mechanics also have a continuous energy spectrum, but bound states have a discrete energy spectrum, which is contrasted to classical physics where that just doesn't happen. One of the early indicators of energies being discrete came from spectroscopy. So spectroscopy basically is the science of the analysis of light emitted by certain materials. When I was a kid, it was popular to do spectroscopy studies of hair to learn about potential like health issues, right? So they would take my hair, a little bit of hair, they would burn it or heat it up and examine the light coming from that hair. And spectroscopy emerged, yeah, and from that light, they inferred what kind of chemicals are abundant or deficient in my body, something like that. So spectroscopy is the study of matter through light. Different chemicals emit light at different distinct, i.e. different discrete frequencies, right? So spectroscopy is really the study, this is my own definition, not official, the study of light emitted by matter. And it's a very powerful tool in learning about the chemical composition of matter. We study spectral signatures of light from the sun. From that, we infer what kind of elements are present on the sun. They studied spectral signatures of light emitted by my by pieces of hair that they burned. And from that, they inferred chemical composition. So Balmer in 1985, he was studying light emitted by hydrogen, hot hydrogen gas. And he found that hydrogen emits light at certain discrete, separate and individually unique wavelengths. Just from studying data he would get a series of numbers. Wavelength 1, that's this way. First wavelength had this value, second wavelength had this value, third wavelength had this value, and he fitted an empirical rule. Empirical means not based on any kind of a theoretical explanation, but just by fitting a curve. Empirical really means fitting a curve. And his empirical rule was the following: 1 over the wavelength of light that he observed was given by approximately, I'm going to put approximate 1.1 times 10 to the minus 7 inverse meters. This is, after all, inverse length, times the following empirical rule: 1/4 minus 1 over n squared, where n was 3, 4, 5, and so on. This thing right here came to be known as a Rydberg constant. And so really you could, sometimes we use letter R. I'm going to use letter R, not to be confused with Gat's constant. And so 1 over wavelength is approximately, well, it equals, this is an approximate value of the Rydberg constant, but it has an exact value. And so with an exact value, it would be given 1/4 minus 1 over n squared. And there was no explanation, but here we already see that light emitted by hydrogen happens only at very specific wavelengths, i.e. at the discrete wavelengths. Trying to understand this formula was a big impetus to development of quantum mechanics and explaining where this discreteness really comes from. Now, what is hydrogen? I'm going to use a 3-dimensional coordinate system. Here's X, Y, Z. Here's a proton sitting at the center. We're going to treat position of the proton as fixed in space. While hydrogen, even if a hydrogen atom is translating overall, we can switch into a co-moving frame in which the proton is translating uniformly. You might say, well, that's not true, because classically, if you think of like Earth and Sun, as the Earth revolves around the Sun also wobbles. Well, you could say proton is really much heavier than electron, so we're neglecting the wobbling. But if you're still fastidious, I will just tell you that there is a way to reduce the 2-body problem into an effectively 1-body problem, where the effective positive charge is sitting, dead still at the center. So don't be bothered by the fact that even classically, the proton is not sitting still, it's wobbling, so it's accelerating. Never mind that. We can rigorously get rid of that effect, and then we can really think of the proton as sitting still. I'm using classical language. And so here's an electron. So after all, the Balmer series of spectral lines were emitted by hydrogen. So one would want to understand hydrogen and the structure of atom in order to understand how it emits light. Now, classical model, so this is negatively charged, this is positively charged, and there's an attractive force. And we discussed that you can relate force to potential energy. So the attractive potential energy is minus E squared over 4 pi epsilon naught 1 over R. you could, so this is a ray R is a radius. You could visualize this in multiple ways. So for example, I can suppress the Z coordinate. So really it's a function of X, Y, and Z, radius in all three directions. But I can suppress, the Z coordinate, and I can plot this. So this is potential energy, suppressed Z coordinate. I'm just trying to visualize this potential energy. It's a function of space as always. And one can visualize this potential energy function as the following landscape, but really it happens in 3 dimensions. Another way to visualize this is to suppress both Y and Z coordinates, and I can just plot potential energy as a function of only the X coordinate, and I would get this kind of a thing. And when you stare at this, you would say, I actually think I know where the discreteness comes from. By this point, you're already familiar with bound states and scattering states. And if you see that this is a scattering state, for which you would expect the solution to the full quantum problem to allow a continuous spectrum. So this corresponds to electron being scattered by the atom, but not captured by the atom. And when you look at this, you can say, oh, this is kind of a well. It's not a square well. It's not a parabolic well. In fact, it's a funny well with a singularity in the center, but it's a well. You would say, well, it doesn't take too much of my imagination to say, well, maybe like all other bound state problems in wells, this would allow a discrete spectrum. Okay, and so you would have different energy levels, right? So this is maybe n equals 1, n equals 2, n equals 3, and so on. And with the experience in quantum mechanics that you already have, you can say, oh, I see what's going on. It's a well, the potential energy is a well potential energy. It goes to 0 at infinity. So it might allow bound states that would have discrete energies, right? So this is an energy of the electron-proton system. And when that system undergoes transitions from n equals 2 to say to n equals 1, for example, you can think of electrons' energy changing from n equals 2 to n equals 1, but it's really the combined energy of the atom. To conserve energy, a light must be emitted, and because the energies are discrete, because the energies are distinct, therefore the set of possible energies of photons that are emitted must also be distinct or discrete. And maybe that explains this formula. And that is the right, really qualitative story. That is actually the right story. But before we get there, so I guess my point is that potential energy, U equals minus E squared over 4 pi epsilon naught, admits discrete bound state solutions. So we're making this statement in retrospect. Now that you've been exposed to quantum mechanics, it's easy to make that statement. But when people first saw this kind of an empirical relationship, of course, they were walking in the woods with eyes closed. they didn't really know about bound states, scattering states, at least quantum mechanically. And discreteness was really a big puzzle. So I'm jumping towards the modern days and I'm explaining this in terms of modern days. So you can say, oh, I see where the discreteness of spectral lines comes from. Because the electron inside the atom can exist at the discrete bound state. And it can make a transition. And to conserve energy, it must emit a photon. And because transitions can only take certain, because the energies can only take certain values, the emitted energies will also take on certain specific, distinct, discrete values. And that explains the discrete values of the emitted photon. So I will come back here. But I wanted to make a couple of comments. So comment number one. This is important. Comment number one. It's a kind of a historical comment, but it's an important comment. When people try to make sense of the structure of hydrogen atom, they, of course, quickly realized that a planetary solution would not work. You would say, why wouldn't it work? This is exactly like the Earth and the Sun. This is exactly like the Earth and the Sun. You have attractive force. What's the difference? That's a really good question. What is the difference? Why the Earth can revolve around the Sun either in a stable way, we're not falling towards the Sun, but with charges, it's a big no-no. Think about that. Well, you see, if electron revolves around the proton, it experiences the centripetal acceleration. So it's actually an accelerating charge. Its speed doesn't change, but its velocity changes. Its speed doesn't change, but the direction of the velocity changes. Acceleration. What do you know about accelerating charges? Well, if you take a charge and you jiggle it, it's another form of acceleration. The electric field pattern around the charge changes. And this changing electric field pattern, if you study this electric field pattern, it would emit waves. Accelerating charges emit waves. Waves carry energy. Emit electromagnetic waves. Electromagnetic waves carry energy. So an electron orbiting a nucleus or orbiting a proton, by virtue of the fact that it's accelerating, it will be continuously emitting radiation and losing energy until it falls into the nucleus. And you can do a quick calculation. You would find that such atoms would not last longer than some very short period of time. I don't actually remember exact value. It's like certainly less than a nanosecond, maybe femtoseconds. So you see accelerating charges. This is centripetal acceleration. Accelerating charges emit EM radiation. They emit radiation. All right, so this would be emitting radiation. And so unstable atom, classical. It emits a radiation, so it loses energy. So electron would fall towards the nucleus. You know what? I will tell you a secret. When Earth revolves around the Sun, actually the same thing happens, but it emits not electromagnetic radiation, it emits gravitational radiation. It emits gravitational waves. So on an extremely, extremely long time scale, Earth would also fall to the Sun. But that would happen on an extremely long time scale, and there are other effects that would render solar system impermanent, other effects that are much more important. For example, the Sun will become a red giant and engulf Earth and so on. That happens on a much quicker time scale. just a few billion years. So gravitational radiation emitted by the Earth revolving around the sun is very, 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 is a negligible effect. But electric forces are much stronger than gravitational forces. And so the electromagnetic radiation emitted by a classical motion of an electron around the nucleus would be a very important effect that would make such atoms very unstable. So it became very clear early on that classical solution does not work. This was a big puzzle that really instigated the development of quantum mechanics. So if we fast forward a little bit, okay, so classical planetary model of atoms does not. Big puzzle. One of the big ingenious breakthroughs was proposed by Niels Bohr. Niels Bohr was a strong advocate of wave-particle duality. And he believed that it's not possible to explain atoms and other microscopic things in terms of classical intuition. And Bohr proposed the following model. It's an early quantum mechanical model. It has its problems. So it's the presentation of what I'm about to say for the next 5 minutes has a sort of a historical significance, but it's also an important thing to mention. So Bohr model of the atom. We must appreciate the fact that these were humans. And as smart as they were schooled in classical physics. So their attempts to explain what's going on, while motivated by understanding that there's something not working with classical picture, it was still grounded in classical physics. So Bohr model, right? So it's like you have a background in something, you see that that something doesn't work, so you have to step away, you have to step up from your experience, but you still have to push off from your prior experience. And so Bohr's model is what I would call a semi-classical model. Or maybe let me use a better word, quasi-classical model. Quasi-classical. But it's important because you will see that, first of all, it explained hydrogen spectral lines, and therefore it had to be taken seriously, but it also suggested that electron cannot be thought of in terms of a particle following trajectories, but it has a wave-like nature. It suggested wave-particle duality. So for this reason, Bohr's model is mentioned in chapter 4 in your textbook. So it's a quasi-classical argument. So classically, if you have a particle following a circular orbit, it experiences a force, right? So this is it's an electric force, right? 1/4 pi epsilon naught E squared over R squared. On the other hand, force equals ma, right? Force equals ma. And if it's a circular orbit, so this is a classical picture. If it's a circular orbit, it has to experience a centripetal acceleration, which is given by m E squared over R. So you can combine the two things and you would find that the velocity of a charged particle following a circular orbit at radius r must be given by the following formula. Okay. Yeah. On the other hand, energy, which is conserved, so it has to be some constant value. So circular orbit of radius r, constant radius. Radius is constant, energy is constant, but energy is made up of kinetic and potential bits. Then kinetic energy is 1/2 mv squared, and potential energy is C above, right? So this thing, potential energy, when we substitute this velocity into the kinetic energy formula, well, we would find that the total energy of a charged particle orbiting at radius r must be given by the following formula. And you don't have to memorize these things, obviously. And again, this is conserved. The radius is a constant. All the other constants here are constants. So this is a constant. But this is in 3D. The force is pointing towards the radius. So this force does not apply a torque. And because it does not apply a torque, the angular momentum is also conserved. Is also conserved. Now we usually use L for angular momentum, and that's a constant. So angular momentum is a vector, it's a constant. So this, for one thing, this means that electron has to revolve in a certain plane with a certain radius. And we know that angular momentum in such a case would be given by this formula. Okay, well, you have two conserved quantities, one energy, which is given by this, the other is angular momentum. Well, very good. So we know V, we know R, we can plug in, we can calculate L. So here's Bohr's idea. Bohr said that angular momentum is not only conserved, but it is also quantized, discretized, takes on only certain distinct values. That's where he injected the discreteness, which is a purely quantum idea. Again, this is not a rigorous argument. This is a semi or pseudo-classical, a quasi-classical. So far, this is a classical idea. And we know that purely classical model doesn't work. So this is where the departure from the classical model is proposed by Bohr. So if it's quantized, he said angular momentum can only take on certain specific distinct values where n equals 1, 2, 3. That's a departure from classical idea. Classically, you can have any angular momentum that you want. Therefore, you can have any, this product can be anything. Bohr said, no, not anything. Well, let me first follow this through. Well, so this says that therefore mvr equals nh bar. Let me label this like this, and this is like this. So this says v equals nh bar over mr. Okay. Combine with formula star. So we can eliminate the velocity, and we would get that radius must also take on only very certain specific values. Now, to be complete, let me give you the formula for the radii. N equals 1, 2, 3. So therefore, this says that electron can only occupy very specific radii. Not a classical idea. It follows from this, not classical idea. And the lowest radius, well, I think it's better to call it A sub B. It's also known as Bohr radius. And it's approximately 0.053 nanometers, 0.5 of an angstrom. Now, when you plug this R into this formula for energy, you would get the following formula, minus m e to the fourth, 2 times 4 pi epsilon naught squared over h bar squared, 1 over n squared. This whole glob of constants evaluates to approximately 13.6 electron volts. So you get minus 13.6 eV over n squared, where n is again 1, 2, 3. So boom, out comes the discreteness of energies. That energy values can be discrete, n equals 1, equals 2, equals 3, and so on. And it turns out that this formula predicts a set of possible transitions. Therefore, a set of possible energies that can be emitted when an electron experiences transition between these energy values, and therefore a set of possible wavelengths. And it predicts exactly the right formula that matches Balmer's expectation for the case when the electron falls down to the third energy level. I will come back to that in a second, but I want to make an argument. All over this argument, all over this strange pseudo-classical argument, it's written all over the wall that there is a wave-particle duality lurking here. For one thing, why would the radius take on only specific distinct values? That's not a classical idea. We can try to understand quantization of angular momentum by saying, what if an electron was described by a wave? At that point, nobody knew what wave it is. This was pre-Schrodinger. But what if it was described by some kind of a wave? Now we know what the wave is. It's a wave function. But back then, it wasn't clear, like what's waving? But never mind. What if it was some kind of a wave? We have a spherical geometry. So the wave must close in on itself. In 2D, it must be something like this. If there's a wave, this is a two-dimensional version. And you start saying, so you have to fit integer number of wavelengths or as you go around the circle. In other words, the wavelength has to be 2 pi r over n. On the other hand, we also have this de Broglie's idea, which is, again, this is pseudo-classical. It's mixing classical and quantum ideas. People had to do that in early days of quantum mechanics. And therefore, 2 pi r equals nh over mv. Right, so I'm just combining 2 pi r equals n lambda. Lambda is h over mv, is nh over mv. So therefore, rearranging mvr, angular momentum, equals nh over 2 pi over n, or nh bar. So here comes lambda equal L, angular momentum, and equals NH bar. So you see, quantization of angular momentum can be explained by treating electron as a wave and not as a particle that orbits trajectories. But of course, this is a pseudo-classical argument. So some classical notions are preserved here. And this is this wave-particle duality sort of waving its hand. Again, this is an early argument. It's not rigorous. It's mixing quantum mechanics with classical mechanics. But in any case, you can see that we get discrete energies, right? Given by this formula, me to the 4 times 2 times, over quantity 2 times 4 pi epsilon naught squared for h bar squared. Or you can just simplify it like this. And so when an electron undergoes a transition from n initial to n final, because energy has to be conserved, it has to emit photon. And so we can see that delta E equals energy of the photon. Remember this quantum ideas, energy of the photon is h over h times frequency. That's Einstein formula. That's hc over lambda. And when we put in the formula for these energies that Bohr found, we get 1 over lambda equals this bunch of crap right here. But it's a beautiful bunch of crap because it predicts a certain interesting thing, interesting spectroscopic relationship. And this is exactly the Rydberg constant, approximately 1.1 times 10 to the minus 7 meters. And if n final equals 4, if a particle, if n final equals 2, if n final equals 2, a particle falls to the second energy level from third or from fourth or from fifth, we get exactly Balmer's formula. So this was a big triumph. Bohr's ideas had to be taken seriously. This really gave rise to quantum mechanics, the more modern version of which you were digesting the last few weeks. Now, of course, fast forward comes the Schrodinger's equation, wave functions, boundary conditions, and the modern version of this problem must be solved by an honest look at Schrodinger's equation. We don't really have time for that. So in the next section of the video, I will briefly, very briefly, summarize the modern theory of hydrogen atom based on the Schrodinger's equation. And I will also mention I will mention a few things that I would like you to know to get out of this. So this was a pseudo-historical introduction, which I think is fair. And I will just say a few words about the modern theory of the hydrogen atom, which obviously, of course, produces the correct energy quantization formula, Bohr's formula, but not through kind of a hand-wavy pseudo-classical result, but through a fully rigorous quantum analysis. So I'll do that very briefly in the next video. And that would be the end of the class. See you soon.